Hello, I'm Professor Von Schmohawk, and welcome to YU. In the previous lecture, we introduced the concept of rational functions. Specifically, rational functions of a single real variable, x. In this lecture, we will examine the values of x that cause the numerator or denominator of a rational function to be 0. The x values that cause the numerator to be 0 are called the zeros of the numerator. For example, since this numerator is 0 when x is 1, we say that this numerator has a 0 of 1. Likewise, the x values that cause the denominator to be 0 are the zeros of the denominator. Since this denominator is 0 when x is either negative 2 or positive 3, negative 2 and positive 3 are the zeros of this denominator. When a rational function's denominator is 0, the function's value is undefined. Therefore, the domain of rational functions must exclude x values that cause the denominator to be 0. Its graph will therefore have a missing point at each excluded x value. In the examples we have seen, those missing points were the locations of vertical asymptotes. However, missing points don't always correspond to vertical asymptotes. In some cases, a missing point simply results in a hole in the function's graph. So let's see how this happens. The rational function x minus 1 over x has a denominator whose value is 0 when x is 0, and so 0 is excluded from the function's domain, and its graph has a vertical asymptote at an x value of 0. In addition, this function's numerator is 0 when x is 1, and so its graph has an x-intercept at an x value of 1. So the graph of this function looks like this. If we change the numerator from x minus 1 to x minus 1/2, the x-intercept moves closer to the vertical asymptote. Changing the numerator to x minus 1/4 moves the x-intercept even closer to the vertical asymptote. If we continue bringing the 0 of the numerator closer to the denominator 0, the x-intercept will continue to approach the vertical asymptote. However, if we make the numerator 0 identical to the denominator 0, the vertical asymptote and the x-intercept cancel each other, leaving only a missing point in the graph. This missing point in the graph is typically referred to as a hole. A hole is produced whenever a numerator 0 is identical to a denominator 0. In this example, both the numerator and denominator are 0 when x is 0. At an x value of 0, the function's value is therefore undefined, and so 0 must be excluded from the function's domain, producing a missing point or hole in its graph. So as we have just seen, numerator zeros produce x-intercepts, and denominator zeros produce vertical asymptotes, except that when a denominator 0 is identical to a numerator 0, instead of a vertical asymptote and an x-intercept, we get a hole. In this example, it is easy to see that for every value of x, the function's value is 1, except for an x value of 0, which produces a hole. However, holes can also appear in more complicated rational functions, where a pair of identical numerator and denominator factors produce a hole. So let's see how this happens. The function x minus 1 squared is a parabola. If we multiply this function by x over x, the shape of the parabola does not change, but now a hole has appeared in the graph. Since the value of x over x is 1 except when x is 0, multiplying by x over x is the same as multiplying by 1, so the parabola's shape is unaffected. However, since when x is 0, the value of x over x is undefined, 0 must be excluded from this function's domain, resulting in a hole in the graph at an x value of 0. The x over x term can be eliminated without affecting the graph, as long as we continue to keep 0 excluded from the domain. This is necessary since if x over x were eliminated without excluding 0 from the domain, the graph would no longer have a hole. Although the hole may not seem important, the same function with a different domain is considered to be a different function. In this example, we started with the rational function x over x times x minus 1 squared and eliminated x over x. This same function could also be written differently as x times x minus 1 squared over x. However, regardless of how this function is written, we can still eliminate the pair of identical factors in the numerator and denominator in order to simplify the function without changing its graph. We can do this for any pair of identical factors in the numerator and denominator that produce a hole. For example, let's say that instead of the identical factors being x, the identical factors were x minus 3. In the same way that x over x is equal to 1 for all x values other than 0, x minus 3 over x minus 3 is equal to 1 for all x values other than 3. Therefore, these identical factors will not affect the parabola other than producing a hole at an x value of 3. And just like we saw in the previous example, this pair of identical factors can be eliminated without affecting the graph, as long as we keep the function's domain the same. Simplifying functions by eliminating pairs of identical factors in the numerator and denominator can often simplify the process of sketching a rational function's graph. So let's try an example graphing the function x squared minus 4 over x cubed plus 5x squared plus 6x. The first step in graphing any rational function is to completely factor its numerator and denominator and identify all the zeros produced by those factors. Factoring the numerator x squared minus 4, we get x plus 2 times x minus 2. Any x value that causes any one of these factors to be 0 will cause the numerator to be 0. And so that x value will be a 0 of the numerator. Since the first factor is 0 when x is negative 2, Negative 2 is a numerator 0. Likewise, the second factor is 0 when x is positive 2, and so positive 2 is also a numerator 0. To factor the denominator, we start by factoring out the common factor x from each of the three terms. Once we have factored out the x, the remaining quadratic expression x squared plus 5x plus 6 can then be written as the product of two linear factors, x plus 2 and x plus 3. Just as with the numerator factors, any x value that causes any one of these three factors to be 0 will cause the denominator to be 0. And so that x value will be a 0 of the denominator. Since the denominator is 0 when x is 0, an x value of 0 is a 0 of the denominator. Likewise, since the second factor is 0 when x is negative 2, negative 2 is also a denominator 0. And since the third factor is 0 when x is negative 3, negative 3 is also a 0 of the denominator. Since any of these three x values cause the denominator to be 0, all three values must be excluded from the function's domain. Now we can check for identical pairs of numerator and denominator zeros. Since negative 2 is a 0 of both the numerator and denominator, we know that the graph has a hole somewhere with an x-coordinate of negative 2. We can now simplify the function by eliminating the pair of numerator and denominator factors that produced the hole, as long as we keep negative 2 excluded from the domain. Failing to exclude negative 2 would eliminate the hole, thus producing a different graph. Since we are keeping the domain the same, we can eliminate the pair of x plus 2 factors in the numerator and denominator in order to simplify the function without changing its graph. Now that these factors have been eliminated, the numerator has a single 0 of positive 2, and the denominator has zeros of 0 and negative 3. Since we have eliminated all factor pairs that produced holes and reevaluated the zeros, any remaining numerator zeros will correspond to x-axis intercepts, and any remaining denominator zeros will correspond to vertical asymptotes. So the numerator 0 of positive 2 is the location of the graph's x-axis intercept, and the denominator zeros of 0 and negative 3 are the x-coordinates of vertical asymptotes. We can now get a rough idea of the shape of the graph by calculating the function's values at a few selected points along the x-axis. We can start by calculating the vertical position of the hole. Since the hole's x-coordinate is negative 2, we can set x equal to negative 2 to calculate the vertical position of the hole. So when x is negative 2, the value of the simplified function is 2, and so the hole's coordinates are negative 2, 2. We know that the graph must pass through this hole. But we don't know if the graph approaches the asymptotes in the positive or negative direction. Since there are no x-axis intercepts between the two asymptotes, the graph can't cross the x-axis between the asymptotes. The graph must therefore grow in a positive direction as it approaches the asymptotes. Next, to estimate the shape of the graph left of the asymptote, x equals -3, we will calculate the function's value when x is -4. So setting the value of x to -4, we see that when x is -4, the function's value is -3/2. So the coordinates of the graph at that point are -4, -3/2. Since the graph must pass through this point, and there is no x-axis intercept in the region, the graph must stay below the x-axis, approaching the asymptote in the negative direction. Next, we estimate the shape of the graph to the right of the asymptote x equals 0 by calculating the function's value at a point to the right of the graph's x-intercept. Setting the value of x to 4, we see that when x is 4, the function's value is 1/14. The coordinates of the graph at that point are therefore 4, 1/14. So we have determined that the graph passes through this point and intersects the x-axis at an x value of 2. However, there are two possible ways that the graph could approach the vertical asymptote. The graph could reflect off the x-axis, growing infinitely positive as it approaches the asymptote, or the graph could cross the x-axis and then grow infinitely negative. We can determine which of these possibilities is correct by calculating the function's value when x is 1. Setting the value of x to 1, we see that when x is 1, the function's value is -1/4. The coordinates of the graph at that point are therefore 1, -1/4. Since the graph passes through this point, we know that the graph crosses the x-axis at the x-intercept and approaches the vertical asymptote in the negative direction. So the graph of this function looks like this. This example shows that the values excluded from a function's domain can either be the x-coordinates of vertical asymptotes or the x-coordinates of holes. So far, we have seen that when graphing a rational function, if there is a pair of identical factors in the numerator and denominator, then both factors can be eliminated as long as we keep the function's domain the same. But what if there are multiple copies of one of these identical factors? To find out, let's look at a couple of examples where this happens. Let's say that we would like to sketch a graph of the rational function x squared plus 6x plus 9 over x squared plus 3x. As we have seen, the first step is to completely factor the numerator and the denominator. The second step is to then identify all the numerator and denominator zeros. Since an x value of -3 will cause either of the numerator factors to be 0, -3 is a 0 of the numerator. Likewise, since an x value of 0 will cause the first denominator factor to be 0, and an x value of -3 will cause the second denominator factor to be 0, 0 and -3 are denominator zeros. Since these x values cause the denominator to be 0, 0 and -3 must be excluded from the function's domain. Now we check for identical pairs of numerator and denominator zeros. Since -3 is a 0 of both the numerator and denominator, we know that the graph has a hole somewhere with an x-coordinate of -3. We can now simplify the function by eliminating the pair of numerator and denominator factors that produced the hole, as long as we remember that -3 must continue to be excluded from the domain. The numerator still has a 0 of -3, but the denominator now only has a single 0 of 0. Since we have eliminated all factor pairs that produced holes and reevaluated the zeros, any remaining numerator zeros will correspond to x-axis intercepts, and any remaining denominator zeros will correspond to vertical asymptotes. So the denominator 0 is the x-coordinate of a vertical asymptote, and the numerator 0 is the location of the graph's x-axis intercept. Therefore, in this example, the x-axis intercept is also a hole, so the graph of this function looks like this. Now let's look at one last example with the rational function x plus 3 over x cubed plus 6x squared plus 9x. Since this function's numerator is already in its simplest form, we only need to factor the denominator. We first factor out the common factor x from each of the 3 terms. The remaining quadratic expression x squared plus 6x plus 9 can then be written as the product of 2 linear factors, x plus 3 and x plus 3. We can now identify all the numerator and denominator zeros. When x is -3, the numerator is 0, so the numerator has a 0 of -3. Likewise, in the denominator, x values of 0 or -3 will cause the denominator to be 0. So 0 and -3 are denominator zeros, and therefore must be excluded from the domain. Next, we check for identical pairs of numerator and denominator zeros. Since -3 is a 0 of both the numerator and denominator, we know that the graph has a hole somewhere with an x-coordinate of -3. We can now simplify the function by eliminating the pair of numerator and denominator factors that produced the hole, as long as we remember that -3 must continue to be excluded from the domain. Since this simplified function's numerator is a constant, no value of x will cause the numerator to be 0. Therefore, there are no remaining numerator zeros. However, this function still has the same denominator zeros as before. Since we have eliminated all factor pairs that produced wholes and reevaluated the zeros, the remaining denominator zeros correspond to vertical asymptotes at x values of 0 and -3. However, we have determined that there is a hole at that position. Although this may seem strange, this is not a contradiction. A hole is a missing point in a function's graph, and so is a vertical asymptote. A vertical asymptote is simply a hole which a graph approaches while growing infinitely positive or negative. So this function's graph looks like this. In this lecture, we have seen how identifying a rational function's vertical asymptotes is an important step in sketching the function's graph. In the next lecture, we will see how to identify several other types of asymptotes that can also be extremely helpful in graphing these functions.